This video is going to give you guys an example of how to do bar charts to account for energy storage and transfer. I want to remind you guys on this first page here, we've got a note that energy transfer occurs when change in a system occurs or between systems. So no energy transfer ever typically happens unless there's a change that's observed or you infer it happened. You also have to remember your guys' bar chart models should show conservation of energy. Energy just cannot be destroyed. It cannot disappear. It can't appear out of nowhere without any explanation. And your bar charts can model that and communicate that. I'll run you through a couple examples. If you get to the point where you can pause it and try the bar chart on your own before I show you, you should try doing that. In this first example, if you guys look at the scenario, I said here are two similar phenomena, but two different systems. So you guys have to be aware the bar chart model has bars that you're going to normally stack your energy to judge how much relative amount of energy storage you have. And then the circle is what I call the system circle. And that's going to be the objects contained in your system, and the energy contained in those objects gets put into the bar charts. Any energy transfers from other objects, you need to be showing arrows into the system circle or out of the system circle. So let's assume also in this scenario that rolling objects are basically frictionless, and so we can ignore any sort of friction and rubbing ideas. Therefore, we're going to not worry about any change in temp, which means there's going to be no change in EQ, no thermal energy changes. I've got all my storage categories down here in the bottom. I can tell in this video or in the example above that I have a spring, a ball, and I have the ground. And the ground is 0 meters at the point where the ball starts off, so there's no height to the ball yet. I know that it looks like there's going to be a speed change and a height change. That means I'm probably going to be using elastic energy storage for the spring. I'm going to be using kinetic energy for the motion, and I'm going to be using gravitational for the height change. Again, no change happens without a transfer of energy. So now we have to track those transfers. In the beginning state, initially, the ball is not moving. That's what the dot above the ball means. The spring is compressed, let's assume. And then in the second state, the ball is in motion, still at 0 meters on the ground of height. And then finally, there's a height increase and a speed decrease. Let's take a look at our system. We have the ball, the ground, and the spring. So any energy associated with those objects has to go into the bar chart. So since the ball's not moving, I'm not going to put EK. Since the ball is at 0 meters of height, I'm not going to put EG. I'm only going to load this up with elastic energy because the spring is compressed. In state 2, there's been a change. You must account for that change. There has been a motion change, so speed has increased. No height change yet. So I'm going to assume that at this point, the spring has fully released and transferred its energy and is back to a resting position. So I'm going to assume that now that elastic energy has been transferred into kinetic energy. And again, we're going to ignore friction for such a good rolling object. In the third state, it's still in motion, but now we have a height change. Height has increased. So now I got to take that elastic energy that got transferred into EK for kinetic, and now I've got to start sharing that energy to the other changes. So there's still motion energy. I have 10 amounts here. I had 10 amounts starting, so I must show that so I can show conservation. And then in the final, there's a height increase. We don't know exactly how much of the 10 amounts of EK gets transferred between them. I'm just going to make an easy judgment and say like it's half and half. Half of the 10 from the EK in the second state gets stored as EK again, but then the other half is in EG. So let's do about 5 for EK. And I'm going to do about 5 for EG. The bar chart is a great model to show changes that occur and account for those changes with the energy idea. So in this case, I've got all my energy accounted for. I started with 10 with the elastic energy stored in the spring. All of it transferred to EK, assuming no friction and no height change yet. And then finally, the change in EK with the decrease in speed and the increase in height. So EK better decrease and EG needs to increase based on those changes. Now let's look at the same scenario down below, but here I've changed the system circle. In this system, it's only the ball and the ground. There is no spring. So these are going to look similar, but yet different in terms of tracking the energy. If we only wanted to track the ball in its reference to the ground, we would not include the spring here. So I would not put E elastic in the beginning because the spring's not in the system. The ball is moving in the in the second state. So I'm going to load it up with EK, like the top example. But conservation of energy says we shouldn't just have energy showing up out of nowhere or disappearing. If you look at state 1, there's no energy. State 2, there's been a change in speed, so the ball is in motion. These 10 amounts of energy have to come from somewhere. So most of you will say it came from the spring, but the spring's not in the system. So we have to show that with a transfer arrow going into the system circle and label it with the object. Do not label it with any of the energy storage category abbreviations like E-elastic, like EEL. Don't do that. Put the object it comes from. So I'm going to put spring. And I'm going to put a 10 on the arrow so it shows how many amounts or units go in. 10 in, and now we're kind of back to where we were earlier. The spring has sprung and transferred all of its energy out, and now we're going to assume once again that 5 amounts of EK and 5 amounts of EG still exist. The only difference in this scenario is that we weren't including the spring. You got to show the energy coming in from another system, the spring system, into the ball and ground system. That's one example. In this second example, I've changed the situation slightly compared to the first example with the ball rolling. In this example, we've got 2 similar phenomena, but with 2 different systems once again. In this case, we have a block, not a ball. So with the block, we have to assume and infer that rubbing between the block and the ground increases the temperature during that friction phase while it's in motion and rubbing. So if there's a change in temperature, we know we have a category associated with that for thermal energy. So I'm going to run you guys through both these. You might want to pause the video and actually give this a try on your own, whether it's in a notebook or in your head. So for the first example, we got the block, the ground, and the spring in the system. Similar to the last example, I'm going to load this thing up with elastic energy. And make sure you're labeling these as best you can. Sometimes I'll forget, and I understand that, but for this purpose here, make sure you're labeling this as you're starting to learn how to use these bar chart models. From first state or the initial state over here to the second state, there's been a change. The block has slid into motion across the ground. So we know there's rubbing going on. We know it's in motion. I'm going to assume the spring is fully back to its original resting position. It's not compressed anymore. So I'm not going to put elastic in here. I'm going to put some EK, but not all. The last example, we loaded it up with EK because there's no friction. Here I'm going to put 9 amounts to EK. But then I have to recognize there's rubbing that goes on between here, the first state and the second state. And that rubbing causes change in temp to the bottom of the block and likely to the ground. And that energy doesn't disappear. When people slide a box across the ground that slows to a stop, people say things like, the energy got used up. That's not necessarily appropriate to be saying. The energy got transferred to storage categories that just maybe aren't that desirable to have for a box sliding. So we have to account for that by putting some amount into EQ. So I'm going to put one amount to EQ. And now I have all 10 of my energy amounts. Nothing has disappeared. Nothing has appeared out of nowhere. Now the change from state 2 to state 3, we've got ourselves a situation where the height has changed, the speed has decreased, there's more rubbing going on, we have to assume, between here. So I'm thinking that EK better decrease. EG needs to show up as a storage category because there's height increase. And EQ is likely going to increase due to more rubbing. So this can be tricky. I'm just going to start with the obvious. I'm going to increase EQ. So we got EQ there. I'm going to increase and add EG for the height change. So I've got 4 out of my 10. That means I have 6 left over that I'm going to associate with EK. Now, some people might be asking, well, how did you choose these numbers? I'm just ballparking them. There's no really big judgment I can make to know if EG's outcompeting EK or EQ. We just don't know until you get into more complex understandings of energy and calculations of how to calculate energy. So these are just relative changes. Normally, I might nitpick this and actually judge like a maximum height to the lowest height and see if the block is halfway between. But we don't have that right now, and that's not the purpose of this video. I'm just trying to show you the basic transfers and storage of what a bar chart shows you guys. So again, I'm going to show you the next one down below, but pause the video to make your own adjustments if you need to in your notebook. So similar scenario, different system. Here we're only tracking the block and the ground once again. So no spring. So therefore we're not going to load anything up in the first state. No elastic energy. People will do that all the time because they see the spring, but we're not tracking the spring's energy storage at this moment. It's not in the system. So that means I'm really just going to replicate what I did before. From the initial state to the second state, there's been rubbing with the ground. There's motion. So I'm going to put EK. I'm going to put EK and a little bit of EQ again due to the rubbing. Make sure you guys try to label your boxes and your bars. Now I've got 10 energy amounts in here to EK and EQ. That energy just can't come from nowhere. So like our previous example of the ball rolling, I have to explain and show an arrow transferring into the system, not from any energy storage category. Do not put E, EL. Do not put an E category. Put an object, and that would be the spring. And I'm going to put 10 amounts. The final state, once again, we have height change, speed has decreased, and there's more rubbing going on between the box and the ground. So I'm going to replicate what I did above, increase EQ due to the rubbing. I'm going to increase EG due to the height change. And then I'm going to take the leftover and put it as EK for the motion. In the next example I'm going to run you through, I want you guys to pause the video, try your own bar chart. All the storage categories are listed over on the right. And then I will show you now my interpretation. So you guys can imagine we've got a ball. It's at rest at some height above the ground. And the ground is the line down at the bottom where it says ground equals 0 meters. So the ball is in, it has height. The dot means no motion, but then the ball falls at two different moments. And the speed increases as it falls towards the ground. While it falls, other changes occur, like the height decreases. So we've got a speed change and we've got a height change. That means I'm likely going to be living with the gravitational energy changes and the kinetic energy changes. I'm not worried about thermal energy because there's no perceived change in temperature, so I'm not going to worry about it until there's a change in temperature. So for the first state, I'm just going to load it up with EG, gravitational energy due to the height. Now there's been a change between state 1, or the initial state, and state 2. The height has decreased. That means EG better decrease over here. So I'm going to decrease it. And this is about where I'm going to make a judgment. Here's the maximum height. This is about halfway to the ground. So I'm not going to put it just half and half in terms of like the EG having 10 and then 5 over here. I'm actually going to put it up at like 7. Because it's like 70% of the way or 60% of the way from the max height. So height has decreased, EG better decrease. But the other change, remember, no change happens without a transfer of energy. The other change is a change in motion. Speed is increased between the initial and final, or the initial and the second state. So I'm going to put a little bit of the leftover into EK. And I'm not assuming any friction for the wind. I'm just going to do a basic scenario. So I started with 10. A change has occurred. I still have 10. It's just they're divided up into different storage categories. So energy is still conserved. In the second state to the final state, there's a change that occurs also. We've got a decrease in height and a speed increase. So now when I get down here close to the bottom, I'm really only going to put like one box, one amount for EG. And then the rest of it I'm going to say is EK. And there's no other category that makes sense to pick in this example. It's really just a height change and a speed change. I'm not worried about temp change. There's nothing compressing or being stretched out for elastic. There's no perceived chemical change. Nothing new is being made. Electrical transfers, I don't see anything that indicates that, or even radiant light energy being released off of this object. So check your example, see if it matches mine. In this final example, I'm going to describe it to you, and then you should pause the video and try your best to fill out your bar charts for this scenario. So imagine a sample of water and a glass or a beaker on a hot plate for some amount of time. Look carefully at the details. In the first state, the hot plate is off. The second and third state, it's on for some amount of time, and I'm going to kind of assume they're equal amounts of time between them. So in the first state, we got the water in the glass as the system. If you notice, the hot plate / burner is not part of the system. Now, I know temperature of the water is likely going to change, so I'm going to go ahead and assign some amount of EQ. That's the only category that really makes sense right now. When I look at the list, yes, the water has some height, but I'm also making my life easy. I'm going to say that the top of the hot plate is the 0 meter mark. I don't see that beaker of water changing height and falling down. So I'm going to make my life easy and say 0 meters is at the bottom of that beaker. I don't see the beaker flying around the room. The thermal energy is likely going to change based on it being on a hot plate. My background experiences tell me so. I don't see anything being compressed or stretched. No chemical changes occurring that I can tell where something new is being made. And again, electrical energy in the water and the glass, there's no indication that anything's changing with that. And the same thing with radiant energy. I don't perceive any light energy being released off of this glass and water sample that wasn't there previous to this setup. So if the hot plate has been on for some amount of time, I'm going to assume that this has been on for a while. It's just at the start it was off. Let's just assume that. And so it's been on for some amount of time. I'm going to assume the temperature has changed. And if you guys haven't seen the triangle to mean change in, I'm going to name drop it here. Change in T, so that means change in temperature. That means I'm going to assume that there's been some increase in EQ. Sometimes these changes in temperature can also come from things like light bulbs, the sun, or other objects that are hotter that can transfer energy from hot to cold. Now, in the first state, I have one amount of EQ. In the second state, I have 4. That means there's a difference of 3. Conservation of energy says that we should have a way to account for where that energy came from. So when you guys tried your bar charts, if you pause the video, you should be thinking even right now that the only thing that could change that temperature in our scenario logically is the hot plate. So in order to account for this missing energy, you must put an arrow transferring in to the system circle, and it needs to be an object. So I'm going to say the hot plate. And it looks like 3 amounts in my example. And again, if you're asking how am I choosing the amounts, these are just relative judgments. I'm concerned about if something has increased or if it's decreased. I'm not necessarily worried about the number that you guys assign to them. I want to know, are you following the pattern or the trend of what should increase or what should decrease? Or if there's no change, then there's no change. Just relative judgments for the amounts. Let's assume some equal amount of time has passed. The water's still on the hot plate. I'm going to assume a change in temp has increased. I increased by 3 before. So now I'm going to increase by 3 again, just assuming it's an equal transfer. You must associate and challenge yourself to figure out where did that energy come from. We had 3 more amounts, likely come from the hot plate. And this is the simplest version we can come up with right now without getting too complex. And I'm just going to abbreviate it HP for hot plate. Check out your work you did to my work.